Hi friends, welcome to my channel. Let's have a look at a newly appeared problem, problem 2524, maximum frequency score of a subarray. In this video, we're going to explain a method or solution based on the sliding window technique. So first I'll read through the problem statement to digest the requirement, and then we do the analysis and explain the code line by line. First, let's look at the problem statement. We are given an integer array called nums and a positive integer k. The frequency score of an array is the sum of the distinct values in the array raised to the power of their frequencies, taking the sum modulo this constant. So here is an example. For example, in this one, 5 appears twice, and 4 appears 3 times, and 7 appears once. So this is the frequency score, that is 96. So we are required to return the maximal frequency score of a subarray of size k in nums. So we should maximize the value at the modulo operation and not the actual value. So here it emphasizes that a subarray is a contiguous part of an array. So here are two examples. So example 2 is sort of special because all the elements are the same. So in other words, we just need to consider this number to the power of 4, right? So that is 1. So in the first example, so we can consider this one, 1 to the power of 3. So this one, this part is 1 to the power of 4 plus 2 to the power of 1, that is 3, right? So this one is the same, and this one is 2 to the power of 4, 2 to the power of 2 plus 1, that is 4 plus 1, that is 5. So we return 5 in this example. So the constraints or additional assumptions for this problem are the following. First, k is positive, so this is an important one, and the k is bounded above by the length of the list nums, and also the length is further bounded above by 10 to the power 5, so this is the constant. So the element in the list is bounded in between 1 and 10 to the power 6. So this is the statement and the additional assumptions. So here we're going to do this problem by sliding windows. Essentially, we need to check each length k piece. So the point is how to compute the frequency score of the length k subarrays efficiently and dynamically. So that's the point we want to make it clear, to make clear in this coding part. So first step, so I'm going to write a wrapper to use cache when we compute power, right? So the power function actually can accept the modulo operation, but here we want to also incorporate a cache. So this is actually simple. So this is the decorator for this function. I'm going to call this function f. So we accept a base, and let's see, we accept a positive integers k, and also we want to do modulo, right? So let's use keyword argument. So this is 10 to the power 9 plus 7. So this is the default value. So what we are going to do is just the return power of a k modulo this constant, right? So this way we finish the first step. So this is just for some preparations. So next, so we do some routine preparations, like first, so we get the length of this nums. This is just for convenience, and also we can initialize a dictionary. So we're going to consider the state of dictionary for each length k piece. First, we consider the first k elements, right, as a base. So for I in range k, right? So we want to do this, the nums I. So we want to increment its frequency by 1. So we need to use this function if we want to write the code in one line. So we get this frequency if the nums I does not exist in the dictionary, so we regard its frequency to be 0, then we add 1. So this way we get the first length k subarray and the corresponding unique frequency, a unique element and their frequencies. Then we can have a reference value. Let's call it current, right? So the current will be the sum of k raised to the power value for k and value in d atoms, right? So actually we can modulo this by this number, large number. So let's do this just to make sure. So it's in the sense of modulo this number. So let me add a parenthesis. So this is the current, and then we are going to do the sliding window. So let's call this sliding window. First, I'm going to introduce another variable, which is the final state of this variable. Result is what we want to return. The initial state will be the current, right? And then we are iterating from the index k to the last, that is n-1, right? Then the element to pop off or get out of this window, and the element to come into this window is nothing but nums I minus k, right? The oldest one, and the current number to be entering the current window, right? So first, if A and B are the same, then if we pop the A and add B in the window, so the dictionary does not change. Therefore, the current state does not change. So we just continue. So this is the one case, right? Another case is that A and B are not the same, right? For sure, A is already in the previous in the current state of D. So we want to consider, we need to monitor how the current change, right? So first, the power of A is decremented by 1, right? We need to first consider that change. So let me write it like this. Consider the power change of A, right? So for this, let's consider two cases. First, if dA equals 1. So in this case, if A is popped out from this window, then there's no A exist, right? Then the current minus, so we need to minus this A. Nothing. Then we just delete this key in the dictionary. So this is one case. Another case is that the frequency of A is larger than 1. Then if we decrement it by 1, we still have a contribution. So in this case, first, the original power is nothing but F A dA, right? Right. So then we decrement this A, the frequency by 1, but the power is still not 0. Then we need to add up, right? Again, so it's A dA. So this is a contribution or change made due to the power change of A, right? Another case, another consideration is consider the power change of B. So there are two cases. First, if B not in the dictionary yet, so then we just add to the window and just add this one. So the current incremented by B, and the frequency equals 1, right? Because it's initially not in. Otherwise, so the power of B will be incremented by 1. Notice that here is decremented by 1, right? So the current, first let's minus this FB dB, and then we modify the power of this B by increment by 1, and then the contribution of B is like this, right? B dB. Notice that the dB here and here have different states, similar as here. So notice that this 3 line of code, so here is minus. So this 3 line of code here is plus. So they are in parallel, but one is decrement, and due to A is to be popped, and B is here is increment due to the fact that B is to be inserted to the window. So you can think like this. Actually, these things are done on the air, right? And then afterwards, what we're going to do is to modulo this by this constant 10 to the power 9 plus 7. And then what we're going to do is that we update the state of the result, and the current, right? So afterwards, after the for loop, so we're going to return the result state. So that's the procedure, and also this together forms a solution format to this problem. I guess for now it's good time to test, right? Let's do this. Key error, the nums I plus, and so here, yeah, let me change this so it equals. Let's run this test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the test cases. So I guess with that said, that's about it for this specific problem. So here we used the technique sliding window to do this problem. As we mentioned, here the point is how to compute the frequency scale of a window efficiently and dynamically. So with that said, I guess that's about it for this video. Thank you.